Section 20.1 Crystal Field Theory. Subsection G. Tetractionally distorted complexes. The Jahn-Teller effect. This is a tetractional crystal system. You can view this as a distorted cube. So really, the angles are still 90 degrees, and A is equal to B. So on the bottom, you have a square. Here you have a square. The only difference is this. In the vertical direction, this silence C may be different from A or B. C can be longer than A, and then you have elongated structure. C can be smaller than A, and then you have a compressed structure. But both structures, these two, are called tetractionally distorted complexes, and both belong to the D4H point group. So they both have a C4 principal axis. They have a sigma H plane that contains these 5 atoms, and they also have the inversion center, etc. Of course, they have 4 C2 axes that are perpendicular to the principal axis. And now, why is this tetractionally distorted complexes observed experimentally? Let me show you the energy diagram of the octahedral complex versus this D4H complex. So over here we have OH point group. There we have D4H point group. In the OH point group, dz squared and dx squared minus y squared have the same energy. So these two orbitals are the EG orbitals. And this 3, dxy, dyz, and dxz, they are T2G orbitals, triply degenerate. So now if we elongate these 2 bonds in the z direction, the symmetry is lowered from OH to D4H. That will break the degeneracy. So over here, dz squared orbital has lower energy than dx squared minus y squared. Why is that? Well, it's very simple. In crystal field theory, we view those ligands as point negative charges. So now, if you have a longer distance between this dz squared orbital here and the negative charges, of course, that will reduce the repulsion between the dz squared electrons and these 2 point negative charges. So that will effectively lower the energy of dz squared. And then we observe the splitting. So how about x squared minus y squared? Well, x squared minus squared are not pointing toward these 2 negative charges. All right? So now let's look at this octahedral. Let's view this as the barrier center. All right? So we can draw a dashed line here if you want to. Let's view this as the barrier center between this dz squared and dx squared minus y squared. And then let's say, well, this splitting is delta. I'm going to just call this delta for simplicity, delta. And then dz squared is half delta lower than the barrier center here. Dx squared minus y squared is 0.5 delta above the barrier center. All right? And then now you put 3 electrons into these 2 energy levels. Well, you will see 2 electrons have negative 0.5 delta below this barrier center. Only 1 electron is 0.5 delta above the barrier center. So overall, this 3 electrons in total has a negative 0.5 delta energy lower than the barrier center. So in this case, these 3 electrons have lower energy than this 3. So that means by elongate these 2 bonds in the z direction, overall the electron-electron repulsion is lowered. Now let's look at the triply degenerate dxy, dyz, and dzx. There's also going to be split among these 3 orbitals. But in this case, the splitting should be much smaller than this. So over here, if you look at the screen, this splitting seems to be smaller than this. Well, that's a mistake. That's a mistake. So supposedly we should draw a much smaller splitting over here. Why is that? This is because although dyz and dzx are somewhat pointing to these 2 negative charges, They are not like dz squared. Dz squared orbital points directly to these two negative charges. DYZ, DZX, they have a 45 degrees angle. All right, so this the four lobes in DYZ are pointing toward the YZ direction, not directly to Z. It's to YZ direction. It's just like not pointing towards north. It's pointing towards northwest direction. So that's why this splitting should be much smaller than this splitting. Again, there's still a splitting. Now DXY has higher energy than DYZ and DZX. It's just this effect is much smaller than here. So in this case, you're looking at 9 d electrons. You have 6 electrons here, 3 electrons in these two orbitals. So again, that will cause the splitting of these two EG orbitals. The EG orbitals now become different. They have different energies. All right. So if you look at your periodic table, D9, there's one example, which is copper. So if you have copper 2 plus, that's a D9 electron configuration. So if you look at the transition metal complex of copper 2 plus, for example, copper 2 plus surrounded by 6 aqua ligands, hexa aqua copper 2, and then you will see the structure is not a octahedral structure. It's tetragonally distorted. All right, so with this kind of structure. So again, if you have copper 2 plus in the middle, these two bonds in the Z direction will be longer than the other 4 bonds. All right. Does it have to be 9 electrons? Well, you can have D7. So when you have D7, well, you can put 6 electrons here and then 1 electron in here. So if you put only 1 electron in here, then this electron occupy this lower dz squared orbital. And again, this electron has lower energy than the barycenter. So that also reduces the energy of the transition metal complex. But I want to remind you, when I say D7 and I put 6 electrons here and only 1 electron here, I'm assuming this is a low spin electronic state. So in the low spin electronic state, you put 6 electrons here and only 1 electron here. If it's a high spin electronic state, when you have 7 electrons, you need to put 5 electrons in 5 different orbitals, and then 2 more electrons into 2 of the 3 orbitals here. All right. So there's still gonna be Jahn-Teller effect if you have the high spin case, but because this splitting is much smaller, the Jahn-Teller effect is much smaller. In the high spin case of D7 electron configuration, the Jahn-Teller effect is more significant if you have a low spin electronic state with a D7 electron configuration. All right, so that's why for this D7 we have to specify it's a low spin case. D9, that's easy. If you have D9, you have to put 6 electrons here and 3 electrons in these 2 orbitals. Now, what about D4? We can also observe Jahn-Teller effect when you have a high spin D4 case. So high spin means, well, you have 1, 2, 3 electrons here, and then 1 electron in one of the 2 orbitals here, and that will give you a significant Jahn-Teller effect. So in this case, if you have a high spin D4 case, well, that means, well, very likely the structure of the transition metal complex is tetragonally distorted. It's no longer octahedral, it's tetragonal. This is going to be tetragonal. So how do you get high spin cases? For example, if you have weak field ligands, very likely it's going to be high spin. All right, weak field ligands. And of course, you need to have 3D transition metal instead of 4D, 5D. If you have 4D, 5D, they're going to be low spin. They will be low spin because the overlap between 4D and 5D orbitals and the ligands is much more significant than the overlap between 3D and the ligands. All right, so there are other cases that you may observe Jahn-Teller effect, although small. If you have one electron, okay, just D1. Let's imagine you have just D1. For example, scandium 2+, that's D1. Titanium 3+, that's D1. Vanadium 4+, that's D1. In those cases, well, this one electron can occupy. In this case, I want to emphasize that if you have only one electron occupying one of the three orbitals, it's going to be the dxy orbital. So you're going to elongate the 4 bonds in the xy plane. So if only one electron is here, it's going to occupy this dxy orbital. And you have this case, all right? You have this case. All right, only one electron occupying the dxy orbital. You need to elongate 1, 2, 3, 4. There's 4 bonds, all right, in the xy plane. When this xy plane corresponds to z equals 0, xy plane. Again, why is that? Again, you're going to distort the octahedral structure. You're going to distort the cube to a tetragonal crystal system. And by elongate this 4 bonds, you're going to lower the energy of the dxy orbital. So in this case, if you have only one d electron, this dxy is lower than dyz and dzx. These two are still going to be degenerate, but you just have one lower dxy orbital. You put that electron here. When you have 2 electrons, well, these 2 electrons will occupy dyz and dzx. So in this case, we're going to just put one electron here and another electron here, dyz, dzx. dxy will have higher energy. So in this case, when you have only 2 d electrons, the structure is going to be elongated in the z direction. So when you have one d electron, it's going to occupy dxy orbital. All right? And if you have 2 electrons, they will occupy the doubly degenerate dyz and dxz orbitals. So you have elongated structure. So that's the difference. What if you have 3 electrons? Well, that's there's no Jahn-Teller effect. If you have 3 electrons, they will just occupy dxy, dyz, and dzx equally. It's going to be octahedral for sure, 100%. Now, when you have 4 electrons, again, it kind of depends. You have high spin, you have low spin. So in this case, we have high spin electronic state, and then you have one of the 4 electrons occupying these 2 orbitals. You observe significant Jahn-Teller effect. What about low spin? Low spin case, you have 4 electrons here. You have 4 electrons here. So you have 1, 2, 3, 4. Okay, you put the 4th electron in the dxy orbital. You're going to see compressed structure. Okay, you're going to have dxy lower than dyz and dzx. You will have this dxy doubly degenerate due to the symmetry of this tetragonal point group. And then 5 electrons. Again, if you have 5 electrons occupy the 3 T2G orbitals, this are T2G orbitals. If you have 5 electrons occupying this, well, the energies will be splitted, and you will have 1, 2, 3, and then 4, 5. You're going to see an elongated structure. You'll have dyz, dzx lower than dxy. So you have 4 electrons here, and then 1 electron in the dxy orbital. If you have 5 electrons occupying these 3 orbitals. So you want to maintain the degeneracy between dyz and dzx, and simultaneously you want to put more electrons in the lower energy orbital than in the higher energy orbital. So whenever you can, try to put the electrons in the lower energy orbital while maintaining the degeneracy, the double degeneracy between dyz and dzx. That's why when you have only 1 electron here, you have to put that electron in the dxy orbital. So in this case, dxy should be lower than dyz and dzx. And if that's the case, that means these 4 bonds, 1, 2, 3, 4, these 4 bonds are elongated, all right? And these 2 are compressed. If we look at a tetrahedral complex, is there any Jahn-Teller effect? Yeah, there is also a Jahn-Teller effect, but it's extremely weak because in the tetrahedral complex, I'll let you just picture this in your head. Anyway, none of the 5d orbitals are pointing directly to the 4 ligands or to the 4 point negative charges. So even if there is a Jahn-Teller effect, it's extremely weak. More commonly, we see D9. Well, this is the simplest case. If you have D9, you will have to have this kind of structure. Okay, and one typical example is copper 2+. And then if you have low spin D7 or high spin D4, you will observe significant Jahn-Teller effect. Well,